I'm Yasunobu Nakamura from Tokyo. I'd like to thank the organizers for inviting me to this nice workshop. So Yoran, one of the organizers, told me that I can speak on magnons, not on surface acoustic waves. So I'm not going to talk about surface acoustic waves, but I think I hope my talk will be useful for audience, especially for those who are interested in coupling, say, surface acoustic waves to coherently to some quantum object. So after all, everything is basically harmonic oscillators, not necessarily spins. And so I think, say, analogy between magnons and surface acoustic wave quantum will be quite straightforward. So I'm going to talk about, say, quantum magnonics, where we couple magnon to, say microwave photons or superconducting qubit. And then in the second part, I would like to talk about optomagnonics, coupling between optical light to magnon excitations. So these are my colleagues in the team in University of Tokyo from in alphabetical order from A to Y. And among them, those guys are working on magnons, so magnonists. And so in the first part, the coupling in the microwave domains, Yutaka Tabuchi and Seiichiro Ishino and Dani, who was a summer student from Sherbrooke, worked on that. And Ryosuke and Arto and Koji are working on the optics side. Okay, so our main motivation is to observe and to control quantum mechanics in a macroscopic scale. And especially, we are interested in control of collective excitation in solids. And so, yeah, historically, quantum mechanics was developed from the consideration in the microscopic world, like a single atoms, single photons, single spins, single charge. But now we have learned that we can even do quantum mechanics in a macroscopic scale, especially in collective excitations in solids. So, for example, our superconducting qubit is basically a quantization of surface plasmon polariton in superconducting circuit, and then do the quantum state control. And the same thing can be done in a ferromagnet by controlling magnons, and in say nanomechanics or solid by controlling phonon. And typically, those collective excitations are spatially extended as a rigid mode, and because of that, it typically has a strong or large transition moment and strongly interact with electromagnetic field. Okay, so just one slide for superconducting qubit. So if you make a LC resonator in a circuit, it works as a harmonic oscillator. But in a superconducting qubit, we want to have some amount of unharmonicity. So that's why we replace this inductance with a Josephson junction, which works as a nonlinear inductor, which makes this confinement potential a little bit unharmonic. And that's why we have now non-equidistant quantized levels in this potential well. And then we can safely use the lowest two levels as a, say, effective two-level system on resonance with some electromagnetic field. And the simplest implementation of superconducting qubit would be like that. So this is a well-known transmon qubit. We have two big parts of aluminum. You see this is a millimeter scale. And in between, we have a narrow bridge with a single Josephson junction. So this is actually exactly the equivalent circuit of this device. So we have a tiny junction in the middle, and then big capacitor part in the outer wall. In other words, this it can be understood as a kind of dipolar antenna. So this big part couples strongly to the electric field in the vertical direction. Okay, so and one motivation to study hybrid quantum systems is like that. So we now know that superconducting circuits works pretty well in the dilution fridge and on chip, and to do quantum information processing. however, it only works at the low temperature and at the energy or scale of microwave. And for the communication between two remote places, we definitely need optical photons through optical fibers. And but because of the energy difference between optical photons and microwave photons of order of say 10,000, we definitely need some sort of interface or transducer to transfer quantum information between two different domains. And that's why we are interested in say developing some hybrid quantum systems, because superconductivity never likes optical photons because it has too much energy. Even a single optical photon can kill hundreds or thousands of Cooper pairs and destroy the coherence. So we want to have some interface to, say, mildly transfer the quantum information without killing the coherence in the superconducting circuit. Okay, so in our group, currently we are working on superconducting circuit controlled by microwave or ferromagnetic magnons controlled by microwave or phonons in nanomechanical devices. And we are also interested in combining optical light to those quantum degrees of freedom. And more recent, so these are the devices we are working on. So this is a microwave 3D cavity with a transmon chip inside, or this is a ferromagnetic sphere, and this is a silicon nitride membrane. And I'd like to emphasize that you see these scale bars or centimeters or millimeters, so it's quantum mechanics in millimeter scales. And more recently, we have started working on, say, quantum surface acoustics. We haven't got any, say, serious results, so I'm not going to talk about this today, but I'm very happy to discuss with you personally. Okay, so and one important ingredient here is a nonlinearity of the Josephson junction, or nonlinearity brought by superconducting qubit. Basically, all other modes work as harmonic oscillator modes. And to do quantum information processing, it's really, say, much more convenient to have some sort of nonlinear devices like two-level systems. And in these combinations, superconducting qubit bring this nonlinearity about. And so that's a very useful device to control other quantum degrees of freedom. Okay, so I'd like to now start quantum magnonics part. And so as Vitali already mentioned yesterday, people have been working on spin ensembles as a possible quantum information carrier. So for example, ensembles of NV centers in diamond are put on a superconducting circuit to couple it coherently, and then people store and retrieve quantum information from the superconducting qubit into the ensemble of NV centers. Or we can do the same thing with a rare doped crystal coupled to superconducting circuits. And also in the optical domain, people have been, let's say, intensively working on optical quantum memories using similar crystals, rare doped optical crystals. And there they have also succeeded in storing and retrieving a single photon quantum information with a significantly high efficiency or high fidelity. Okay, so but so far no one has say successfully combined between these two activities. So that's what we are interested in. And but we actually decided not to go into this paramagnetic spin ensembles, but instead to use ferromagnetic spin excitations. So this is our, say, naive idea to use ferromagnetic spin excitations to mediate microwave and optical quantum informations. And so if we compare this with paramagnetic spin ensembles, ferromagnet typically has much more spins inside. So the spin density is several orders of higher because in paramagnetic crystals, they want to isolate spins from each other. So that's why they usually dope spins very lightly, and the spin density is very small. And so the spins inside the crystal are supposed to be independent. So the spatial mode of these spin excitations are basically defined by the electromagnetic field you shine. So if you shine microwave on one part of the crystal, then the spins here couples to the microwave mode and excited. But if you shine laser light on other part of the crystal, these spins will not feel the excitations here, so they don't communicate each other. So in order to develop a kind of quantum interface in a paramagnetic spin ensemble, we have to be very carefully design the spatial mode matching between microwave and optical light. But okay, in ferromagnets, because spins are so dense and so strongly interacting by the exchange interactions, so basically what we can excite is collective modes, like say spin wave. So in this case, because this mode is a rigid mode, like a oscillation in the cantilever or membrane, we can just tap on one part of the crystal with a microwave, and then this is the mode is excited in the whole crystal, and then you can sense the excitation from the other side by using light in principle. Okay, so that's the motivation of using ferromagnet. Okay, so what is magnon? I think you know about it. So basically, magnon is a quantum of spin wave excitations in spin systems. But I like to begin with the very simple example of say two coupled spins, not many spins, just two spins. So if we don't have any Zeeman field, any exchange interactions, then all four spin states are degenerate. And now we switch on the Zeeman field, and now okay, the degeneracy is lifted. And when we switch on the exchange coupling between the two spins, now the triplet and singlet is shifted by exchange energy. And now I'm tempted to call these states as a 0 Magnon state, 1 Magnon state, 2 Magnon state. And if we consider the spatial symmetry, this is kind of a K, the wave number equals 0 mode. And this is spatially inhomogeneous with a basically finite wave number state. You'll see the, say, meaning in the next slide. Okay, so now we consider n coupled spins. It could be, say, one-dimensional n spin systems. And so this is an energy diagram with Zeeman field and without exchange coupling yet. So, the spacing, the vertical spacing is basically the Zeeman energy. But now we have many states because we have many spins. And for example, this column corresponds to the largest, say, spin quantum number states. And then this one has one spin less, and then and so on. And if you look at this particular manifold, which means just a one Zeeman energy manifold, these states basically and okay, so these are basically the states with one spin flipped up. And if you switch on the exchange interaction now, because of the interaction between the spins, now the eigenstates of this energy are like this. So the eigenstates is now a superposition of all the possible spin, one spin excited state, say superposed with some phase factor. And this phase, the K corresponds to the wave number of the spin wave. And the energy dispersion curve of the spin wave is the cosine cosine k basically relations, and the bandwidth corresponds to the exchange energy. And okay, just for the just on purpose, I bring this say 0k zero wave vector state to this column, and so this corresponds to the uniform say spin precession, and others have some spatial structure in the mode. And if you look at this manifold or this column, and now okay, this is a one Magnon state with a uniform superposition of the possible spin excitation state. So now the phase factor is all 1 because it's uniform superposition. And now two Magnon states will be say a superposition of two spin excited states, and so on. And if you look at this column, this is basically equally spaced by the by spacing of the Zeeman energy. So if the energy levels are equally spaced, this is basically say equivalent to harmonic oscillators. So that's why I mean this spin wave excitations or Magnon systems is can be very well approximated by a harmonic oscillator. Okay, yeah. So now this is the material we are using. So this is the complicated oxide called yttrium iron garnet, yttrium 3, iron 5, and oxygen 12. So this is actually very well known ferromagnetic insulator, and it's important that it's insulated, and that means there's no conduction electrons which scatters spin excitations. That's why this has a very long lifetime spin excitations and a narrow ferromagnetic resonance line. And also it's important that this material is transparent at infrared. And it has very strong exchange interactions between the ion spins, and that's why it has a very high Curie temperature. So it's even at room temperature, it's a very nice ferromagnetic material, and it has a high spin density. And this has been known for say more than half a century. So and then nowadays this is applied in many applications like microwave components, oscillators, and filters. And then by using the Faraday effect, it's applied in optical isolators. And then more recently, it is very much used in spintronics research. Okay, so we put the sphere of this ferromagnetic crystal. So this is like a millimeter scale sphere, nicely polished. It's black, even though it's transparent at the infrared. And we apply static field and then the AC magnetic field in this microwave resonator made of copper. And now the spin is driven and starts precessing all together. So this is basically say uniform or k equals 0 spin wave in the sphere. So all the spins in the sphere precess all together uniformly. And in more detail, so we put the sphere at the maximum of this the cavity magnetic field of the cavity mode, and then it's say precess around. So this precession mode is called Kittel mode after Charles Kittel. And we apply static field about 0.3 Tesla to have this precession mode around at around 10 gigahertz. We need 0.3 Tesla, and so created by a pair of permanent magnets, and then with a magnetic yoke, and in addition we put the superconducting coil here to adjust to fine tune the magnetic field. Okay, so this setup is cooled down to 10 millikelvin, so that there's no thermally excited microwave photons or thermally excited magnons. Because magnons at 10 gigahertz correspond to the energy of 0.5 Kelvin. So at 10 millikelvin, it's basically 0 temperature. So there's no thermally excited magnons. And the lines are heavily filtered so that there's no, say, thermal noise coming from the room temperature to the low temperature part. to be in the quantum regime. So if we look at the microwave spectrum, microwave reflection or transmission spectrum of the cavity as a function of the magnetic field generated by the current in the coil. By the way, this 0 is not the zero field. This is on top of about 0.3 Tesla. So the cavity field frequency is around 10 gigahertz, and when we sweep the magnetic field, the Magnon mode moves around, and then here they coincide each other. And then because of the coupling between the cavity photon and Magnon in the sphere, we see the strong anti-crossing. And I'd like to emphasize again that this experiment was done at very low temperature without any thermally excited magnons or photons. Okay, so if we analyze this, so if we take the, say, cross-section of this spectrum and do the fit-in, it's nicely fit by a simple model. And then we see this photon modes and magnon modes, say, mix each other to make a magnon polariton modes. And if we fit these peaks, and then we found these numbers, especially the coupling strengths between magnons photons like 50 megahertz, and the line widths like all those megahertz. So this is in a very, say, strong coupled condition. The coupling is much stronger than the decay or loss. Okay, and so that's good. And we also checked the size dependence of the sphere. So with increasing the volume of the sphere, basically the number of spins inside the sphere increases. So for the 1 millimeter sphere, we have about 10 to the 19th of spins aligned all together. And even though the, say, so okay, from this scaling, we can actually estimate the coupling strength per single spin, and which turns out to be very small, 40 millihertz. But because of the large number of spins inside, it's enhanced by the factor of square root of n to have a order of 100 megahertz coupling. And we can also estimate this single spin coupling strength just by multiplying the Bohr magneton times vacuum fluctuation amplitude microwave cavity, which nicely agree with the experimental result. Okay, and about the decoherence. So this is the old data from Bell Lab in 60s, and showing the temperature dependence of the ferromagnetic resonance line width. And this is the dots are the data they obtained, and actually this is to the by far the best result I have found. The narrowest line width in the ferromagnetic resonance. So they really did a great experiment at that time. So, so you see, it shows a strange behavior like that, and they attributed this to basically three contributions, like temperature-dependent Magnon phonon scattering, but which dies away at low temperature. And this peak is attributed to some inelastic spin scattering by the impurity spins and showing strange temperature dependence. And, but it also disappears at the low temperature. And what's left at that time, 4 Kelvin, is attributed to the surface roughness Magnon-Magnon scattering. Okay, so our naive hope was to see at least a slight decrease of the line width if you go down to the low temperature. But what we found is not exactly like that. So this is the temperature dependence of the line width. The red is the data. So the line width becomes narrower if you go down to 1 Kelvin, but then it turns up and then saturated. So we wanted to have something like that, but it didn't show that. And so we don't know exactly the mechanism yet, but our current interpretation is that the Magnon mode coupled to the ensemble of some impurity spins which has, say, basically the same frequency as a Magnon excitation. And then what we expect is this kind of temperature dependence, say tangent hyperbolic thing. And this is fit in with this function and some offset. So actually, this is nowadays very well known in other systems like superconducting resonators and say glass physics, for example. So ensemble of two-level systems can decohere the say resonator mode. And, yes?
So this is all at basically the single photon level?
Yes, yes, yeah. So if we check the power dependence, we see the line becomes narrower. So it's showing the power saturation effect. So it also supports this interpretation. Okay. Okay. So so far we worked on coupling between the microwave photon mode in the cavity and the Magnon mode in the sphere. But as I said, both of them are harmonic oscillators. And for harmonic oscillators or linear systems, the correspondence between classical and quantums are so nice, and it's difficult to distinguish them indeed. So it would be nice to show some more difference between quantum and classical domains by using a nonlinear or unharmonic object, which is qubit. So in the next experiment, we put the qubit and the REIG sphere in the same microwave cavity. And they're about 3 centimeters away because we want to apply 0.3 Tesla here. We don't want to have any magnetic field here. That's why we put them apart. But still, they can interact each other via cavity mode excitation. So we put the sphere here, qubit there. So in reality, it looks like that. So sphere here, qubit there, and then we combine these two pieces to make the cavity. Okay, so even though they don't interact directly, they can still communicate via the cavity mode. And in this case, they are aligned in the frequency by tuning the magnetic field, but the cavity is detuned by about 2 gigahertz. But still, the qubit and Magnon can exchange the energy quantum by via the cavity mode or via the virtual excitation of the cavity photon. So this is a kind of second-order process which predicts the coupling strength like that. So Gm times Gq over this excitation energy. So, and we expect to have something like 10 megahertz coupling strength in between. And then we would have this beam splitter type Hamiltonian. Okay, we excite the qubit with a microwave and in this continuous wave experiment. And then we monitor the excitation of the qubit by using another cavity mode and what people call dispersive readout, where we see the slight change of the cavity frequency depending on the state of the qubit by monitoring the microwave reflection at this frequency. Okay, so this is the result. So again, we sweep the magnetic field on top of 0.3 Tesla, or so, 0.2 something. And then, so the qubit is at the 8 gigahertz, and the Magnon frequency goes across this frequency. And at this point, they talk each other and show this anti-crossing. And the coupling strength is like 10, 20 megahertz, as we expected. So this is a vacuum rapid splitting of the qubit. But now the vacuum is not a, say, electromagnetic field vacuum. This is a vacuum of Magnon mode. So this is a Magnon-induced vacuum rapid splitting or Magnon vacuum-induced rapid splitting. So we actually what we see is the vacuum fluctuation of this Magnon modes. Okay, we can do the time domain experiment as well. So we excite first the Magnon state, and then the energy quantum is moving back and forth between two of them. Okay, this is the vacuum Rabi oscillations. Okay, and we can also use this qubit as a kind of nice probe to monitor the number of magnons in the sphere. So I said there's no summary excited magnons, but who can be sure about it? So, so here we detune the magnon frequency away from the qubit. So now the coupling is not, say, existing directly, but still the qubit can feel the number of magnon excitations because of this interaction. And the resulting effect is the like a Stark shift of the qubit frequency depending on the magnon excitation strength. So maybe you know Stark shift, which is the energy shift of a two-level atom in say strong electromagnetic field excitation or laser light. And so usually Stark shift, say AC Stark shift, is proportional to the power of the upright laser light. But in this case, because the coupling between them are so strong, this Stark shift is now quantized, not anymore continuous. So depending on the number of the magnons in this magnon mode, the qubit energy qubit spectrum is discretely shifted. So that's what we observe here. So here, without magnon excitation drive, we just see basically the single peak for the qubit excitation line spectrum. But with increasing the magnon excitations in the magnon mode, and now we see side peaks appearing more and more with more excitation power. And if we fit this with a model by J. Gambetter in 2006, we can nicely fit this spectrum and then deduce the number of magnons excited in the sphere. So as a function of the excitation microwave power, what we obtain is basically the, say, Poisson distribution of the number of magnons in the sphere. And now we are sure that we start from the 0 magnon state to 1, 2, 3. Okay, please. Yes, yeah. So basically, as I said, magnon mode is a harmonic oscillator. So if we drive harmonic oscillator with a coherent microwave, what we create is a coherent state of the magnon mode. And that's why we have Poissonian distribution of the number state. This is the coherent state of magnons. Okay, so that's about the quantum magnonics in the microwave domain. So now I'd like to switch into the optics. So optics is not still in the quantum regime. So that's our hope to go reach. So so again, we use the same sphere in same cavity, but now at the room temperature. And another difference is that now we have holes in the cavity so that we can shine the laser beam across the sphere. And then we see by the Faraday rotation, we monitor the magnon excitation in sphere. So in this experiment, we drive the magnon by the microwave. And so not a single magnon. Now it's millions or billions of magnons in a coherent state. And so the spin, say this macroscopic spins now precessing around. And because Faraday effect senses only the magnetization along the optical axis. So it senses magnetization in the x direction. And because it's rotating, precessing, basically this polarization of the light is now oscillating after transmitting through the sphere. And we detect this with a high-speed photodetector and then monitor it. So this is, again, the microwave, say this cavity and magnon spectrum observed in the microwave spectroscopy. So as I said, this is nicely observed even at the room temperature and at high power. And so we see anti-crossing here. And these other small anti-crossings are due to the other magnon modes with a different symmetry in the sphere. When we misalign the magnon, this REIG sphere, to have a little bit inhomogeneous field distribution, we sometimes see these things, but we don't care about that. So we want to focus on this. So in microwave spectroscopy, we see both microwave cavity line and the Magnon line. But now if you look at the optical signal here, simultaneously measured, we see these Magnon lines there, but not anymore microwave cavity line, because Faraday effect doesn't sense the microwave cavity. So we nicely see the Magnon line through the optical detection. So this is a kind of, say, microwave to optical signal transduction in a, say, classical sense. And we can do the opposite way. So here, now we switch off the microwave drive. So there's no Magnon excited. Otherwise, of course, there are some thermal excitations. But now we shine two laser light with detuning corresponding to the frequency of the Magnon excitation. So by doing that, we can actually excite Magnons by stimulated Brillouin scattering. By using this Raman type process, we create Magnon by using the two laser light. So we again, and then once Magnon is created here, because it's strongly coupled to the microwave cavity, it immediately decays into the microwave, and then we can detect the outcome in the microwave. So this is a result. So we see some microwave signal, say coherent microwave signal coming out, and then so this is now the signal transmission from light to microwave via Magnon excitations. But okay, the biggest problem is this efficiency. So this is a quantum efficiency. Quantum conversion efficiency is about 10 to the minus 10th. So we want to have 1, but still very small. Right. So that's say conversion experiment. So we definitely need to improve this number for, say, quantum interface. And now it's a natural idea to use optical cavity to enhance the light spin interactions. So basically, this small efficiency is due to the weakness of the interaction between spins and light. Spins and microwave interact so strongly, as we have seen already, but the spin and light interacts very weakly. So that's why we want to use optical cavity to enhance that. Okay, so now we use the same sphere, but in a different way of optical coupling. So we use a nanofiber, and then we send the laser light through this fiber waveguide. And then this laser light couples to the whispering Gary mode of this around this sphere. Okay, and now recently people have got interested in very special properties of whispering Gary mode. So this is an experiment done in Arno Rauschenbeutel's group in Vienna. So they use a similar, dielectric cavity for the whispering Gary mode, and then send the laser through the optical nanofiber, and then this couples to this and then goes. And they noticed, okay, it's actually known for a long time, but they nicely demonstrated that this whispering Gary mode has, of course, two polarization modes, but one of them, which has a electric field polarization in the equatorial plane, has a peculiar property showing that this E field vector rotates like this when light propagates around the circle. And so this special behavior gives effectively say sigma plus or sigma minus optical polarization along this quantization axis perpendicular to the screen, and coupled nicely to the spin excitation in the rubidium atom nearby the cavity. And similar effect was also seen in the same group in the nanofiber. There's no cavity here, but in the laser mode transmitting through the nanofiber has also a strange polarization behavior. On one side, electric field rotates like that when light is propagating like that, and on the other side, the E field rotates like that. So on the top or bottom, the polarization behaves differently in the nanofiber. So why these things happens? This is a very simple thing, and this is just no quantum mechanics. This is just Maxwell equations. So in Maxwell equations, divergence of E field is 0. But, so usually in a plane wave or in a paraxial approximations, we suppose that there is no gradient in the E field in the transverse direction. So that means, say, electric field along the optical axis is 0. So the light only has a transverse field. But when light is very tightly focused, or for example in the evanescent field, there is a very strong gradient of the transverse in the, say, transverse field. So that means, say, now there's a electric field also along the optical axis. So because of that, this polarization circulate in this, for example, in the evanescent field. And this is something what people often call spin orbit excitation, interactions of light, because optical polarization, say, sigma plus or sigma minus couples strongly to the orbital degrees of freedom or modes of the light. So that's what we see also in our sphere. So now we have a REIG sphere which has a whispering mode circulating around, and which this TM mode has this polarization, say, E field rotating around. So effectively, this is a sigma plus in this quantization axis, and TE mode behaves as a, say, pi polarization of light. Okay, and because of these properties, we can now select Magnon excitation by the angular momentum selection rule. So this is say, Magnon number states, so say creating magnons or annihilating magnons. And G and E is a kind of optical transition in this crystal. So this light couples to this transition. Okay, this is very off-resonant Brillouin scattering, and this Brillouin scattering goes like that or like that. But because of this polarization, we can, and also because of the angular momentum selection rule, we can only go this direction, for example, and then we see in the Brillouin scattering spectroscopy, we see only the red sideband. So if we shine this sigma plus light or TM mode, then it can only emit red sideband, the smaller energy photon. And if we shine TE mode light, then it can emit only a higher energy photon or blue sideband. So we see more than 100 times difference in the sideband signal. And yes, similar, the same thing can affect also in the, say, non-reciprocity of the Brillouin scattering effect. So if we shine the TM mode from this spot, we see very strong generation of the Brillouin sideband. But if we shine the same mode, same polarization from that direction, then the effect is very small. The difference is again more than 100 times, or nearly 100 times. So this can be also understood in the same picture. So if we shine the light in this direction, it corresponds to sigma plus, so we can generate this very efficiently. And if we shine this TM mode from that one, then it excites this and then create this. So it looks, say, the effect looks, say, symmetric or, say, similarly with a similar efficiency. But actually, there's another constraint. So here, this happens for the case where TM mode has a higher frequency than the TE mode, and this happens in the opposite case. But in the real device, because of the geometrical birefringence, TM mode always has a higher energy than TE mode. So that's why this is preferred, but this is not preferred. So that's why we see this very strong asymmetry in the Brillouin scattering. Okay, so this is not really, say, quantum effect, but it's nice to see that this photon chirality interact with, say, gigantic spin in a bulk ferromagnet. Okay, and I'd like to mention that work yesterday mentioned by Florian. So this is also a similar, similarly motivated experiment using electro-optical light conversion instead of magnons. So they want to develop microwave light conversion via EO modulator. And in this case, they use a disk of lithium niobate and embedded in a microwave cavity. And they drive the cavity mode with a microwave and generate this oscillating electric field in this crystal. And at the same time, they shine the laser from this port, and then through the prism coupling, it couples to the whispering gate mode and then emit it. And so by doing that, basically what they see is, say, again, Brillouin scattering light, now driven by this electro-optical effect. And so in this case, so similarly, so they have a free spectral range separated number of whispering gallery modes in this disk. But to have efficient optical to microwave or say optical down conversion, they really want to have say a non-equally spaced whispering gallery mode, because if it's equally spaced and if you drive at the resonance, this is scattered upward or downward equally. So the efficiency would be at most 50%. So usually people drive slightly off resonance to have a asymmetric, say, up conversion or down conversion. But they actually smartly engineer this distribution of the whispering gallery mode in a free frequency spectrum so that they are not equally spaced by using some mode-mode interaction between whispering gallery modes. So in this case, they can drive at this resonance and then only up convert the optical photon when this is on resonance with the microwave drive. So, and by doing that, they actually achieve the conversion efficiency from optical photon to microwave photon, or vice versa, by say efficiency of 10 to the minus third. This is quite nice. Okay, so actually our model is, say, basically same as their experiment. So if you write a Hamiltonian in our, say, Magnon Brillouin scattering experiment, so we have whispering gallery mode TM mode, whispering gallery mode TE mode. So these are light optical mode, and this is a Magnon mode here. And so these three harmonic oscillators interacting. And but they have all different frequencies, so it's not a resonant interaction, but it's kind of a, say, Brillouin type interaction. And so each mode couples to the external mode, light mode or microwave mode, and it has a, say, decay or, say, coupling strengths and so on. So the Hamiltonian can be like three harmonic oscillators coupled to this Brillouin type interaction. But when we, say, apply a strong pump on for example, in this TE mode, then this can be considered as a classical, say, C number, so we can take it out to the front. So now we obtain what we obtain is a harmonic oscillator, beam splitter type interaction Hamiltonian. And if we solve this input-output model, then what we obtain is like that. So this is a conversion from microwave to optics if we apply this pump power here. And then these are basically density of states of each mode, say, Lorentzians. So to have a nice conversion, we have to fulfill this triple resonant conditions to basically for the energy conservation. And but actually, in our experiment with magnons, this condition was not fulfilled because this difference, this geometric birefringence is about 50 gigahertz, and magnon was about 10 gigahertz. So this is far detuned. That's why that's one reason why we observed very small efficiency. But now, so how we can improve the numbers? So we have to fulfill this condition, and then maybe hopefully get a better cavity with higher Q, and reduce sample volume. And maybe we have to use a disk instead of a sphere, and then we hopefully obtain a similar number as electro-optical modulators. But this is of course not one yet. So our hope is to use some other material with a stronger magneto-optical effect, and to enhance more these numbers. Okay, so conclusions. I talked about quantum magnonics with ferromagnetic crystal, and we couple microwave to or superconducting qubit to the Magnon excitation, and then I also talked about optomagnonics, and now we are working on more on say non-classical state control in the Magnon mode in the microwave domain, and also we want to optimize the optical coupling, and for enhancing the say spin light interactions, we are considering another material, which is erbium iron garnet instead of yttrium iron garnet. So let me briefly explain that. So the problem with yttrium iron garnet is that this optical transition of yttrium iron garnet is very high energy, for about 400 nanometer. But we are doing brilliant scattering at 1.5 micrometer. So this is really far detuned Raman scattering, which means very inefficient or weak. So the motivation to use erbium is that erbium has a nice optical transition at 1.5 micrometer. As you know, this is used in erbium doped optical fiber optical amplifiers. So if we have these lines here, then we may be able to do this brilliant scattering in a very near resonant condition, which may enhance the optical spin coupling strength. And so this is again all data from Bell Lab from 60s, and this is optical absorption spectrum of erbium or rare earth iron garnet. And so you see yttrium iron garnet, if you zoom up, has a very transparent, is very transparent around infrared spectral range, but erbium iron garnet has sharp lines at exactly at 1.5 micrometer. So that's what we want to use. And another data from earlier work showing that Faraday rotation is really enhanced at this particular frequency, especially at lower temperature. By some reasons, they measured only at 130 Kelvin, but we want to go down to, say, millikelvins or 4 kelvins at least. So we hope to see further enhancement of the Faraday effect there. And that's what we are currently working on. So we actually grew erbium iron garnet crystal because we cannot buy it. And then we took optical absorption spectrum where, let's say, at room temperature, this, 200 terahertz is about 1.5 micrometer. And then, but with decreasing temperature, the line narrows a lot. And then, because erbium has a number of levels, we have many transitions, but it's good that we see nice sharp transitions. So our hope is to do, say, maybe around this frequency, we do a very near resonant brilliant scattering. Okay, so that's the end of my talk. Thank you very much for your attention. Yeah, so That's we don't know. So that made a big problem. Yeah, so we have to check it by ourselves. Yeah. So I couldn't find any study at low temperature. So we have to pray. Yeah. So I think it depends on the line is of these atomic levels, right? So if the line is narrow, you can approach safely. Yeah, so it depends on the line width, I think. So L beam is known to have very narrow optical line width because it's a 4F electron transition, and so that's our hope. Okay, it looks far away, but still you see it's excited, right? And so yeah, so actually we found that after some detailed calculations, the conversion efficiency from microwave to light here is not maximum at this point. It is maximum maybe here. It's a kind of balance between several things. So maybe that's why it looks like extended more. But basically, say it is excited. So the cavity here is narrow, but it's Lorentzian, having tail.
It's just the tail.
Just the tail. Yeah. Yeah. Right, because this branch is basically a mostly photonic branch. Yeah?
Yeah.
So photonic branch is not well detected by optical light. That's why it's say disappearing. Yeah? The optical light senses magnon excitations, not the photons, microphotons. So that's why this line is mostly gone, but this stays.
Yeah, this is fine, but you have an additional mode.
Oh yeah.
200 milliamps.
Oh yeah.
This spin wave mode.
Oh yeah. But indeed, these spin waves are very weakly coupled to, and also probably because these modes have different symmetry rather than the scatter mode. This mode is the uniformly precession mode, but these small modes could be could have different spatial modes, which may have small overlap with the light mode. Yeah, if you integrate out, then maybe it's gone. Yeah. No, it's a coherent state of magnons. So because magnons mode is harmonic oscillator, if you drive it by coherent microwave, you create a coherent state. So the coherent state is a superposition of the Fock states, and that's why we see say distribution probability of 0 photon, 1 photon, 2 photons, not one, but some superposition. We don't know as it is. Yeah.
say what temperature the sphere is at?
Probably no. Yeah, it looks quite cold. Because we don't see any, say, sideband here. Yeah, we see some sideband here. Actually, this 0, 1 is so 1, 0 is a 1 magnon, and 0 means here is a number of microwave photons in the cavity. So 0, 1 corresponds to the presence of a single microwave in the cavity. So you see the cavity is a little bit populated. Yeah, but by some reason Magnon is not. Yeah. So you mean the loss by this rod? Yeah. We don't know how much loss related to this, say, glue and the rod. But yeah, we don't know.
Other question? If not, thanks to speak again.
Thank you.